velocity triangles for centrifugal pump. Now you can see in this diagram, the velocity triangle for centrifugal pump is completely in the reverse direction to that of our reaction turbines. So you can see this is my inlet velocity triangle, and here is the outlet velocity triangle. Okay, so water enters radially with VI velocity, you can see here. Okay, so that is at angle alpha I equal to 90 degree at the inlet. So corresponding to that, my VRI, so VRI is along tangential direction. Water enters to the vane with velocity VRI in this tangential direction. Okay, and UI is my tangential velocity. Okay, then water leaves at velocity VRO. So correspondingly, we have another components of velocities VO, the whirl components and flow components, and the vane angles. Alpha O, the vane angle is beta O, and guide vane angle is alpha O. So these are at the outlet. Now, in case of centrifugal pump, now beta O dash, that is called the vane angle at the outlet. So depending upon this value of beta O dash, if this beta O dash is less than 90 degree, so my shape of the vane is called backward curved vane. That is called backward curved vane. If this beta O dash, see in another diagram, okay. Now if this beta O dash greater than 90 degree, so that shape of vane is called forward curved vane. Okay. If beta O dash equal to 90 degree, so that is called radial vane. Okay, that is called radial vane or radial curved vane. Okay, these are three different shapes of vanes of the impeller in case of centrifugal pump. Now, next we see the relation for energy transfer. So this is my diagram A, this is B, and this is C. Okay. Now next is the equation for energy conversion. Now this equation contains some assumptions. So my first assumption is that impeller consists of infinite number of vanes. Okay. So this is because the water is guided through the veins smoothly. This is for the water guided through the veins smoothly, then we can assume we have infinite number of vanes in case of the centrifugal pump on the impeller. The second assumption is no energy loss due to friction and eddy formation. Due to friction and eddy formation. And third one is no shock loss at the entrance of the veins. No shock loss at the entrance. So these are my few assumptions to derive this energy conversion relation. So now I can write the energy transfer per unit mass. That I can write as torque into omega. So my torque is VWO RO minus VWI RI into omega, or I can write it as VWO UO minus VWI UI. Okay, and per unit weight, so energy transfer per unit weight, that I can write as VWO UO minus VWI UI divided by G. Now in case of centrifugal pump, so my flow is radial at the inlet. So that means the angle alpha I is equal to 90 degree at the inlet. So at that time, VWI is equal to 0. So now I can write this energy transfer per unit weight as VWO UO divided by G. Okay. Now this energy transfer per unit weight, that is another type of head, and I call it as Euler's head. Okay, this is called as Euler head. Okay, so my Euler head is equal to VWO UO divided by G. So this is my energy conversion equation for centrifugal pump. The next is the variation of Euler head with vein shape. So my Euler head is VWO UO divided by G. Okay. Now you can see from figure A, when my angle beta O dash is less than 90 degrees, say for this case, I can write VWO. So you can write VWO. So VWO is equal to UO minus VRWO. Okay. Now I write this is equal to UO upon G. My VWO is UO minus VRWO. Further, I can write VRWO equal to, so UO upon G, UO minus, so this is VFO cot of beta O dash. Okay. Now I have the formula for discharge. So discharge is similar to that of my reaction turbine, that is pi. At outlet, I can write DO, BO, VFO. Okay. So from here, I can write VFO is equal to Q divided by pi DO BO. Okay. So now put this value into above equation. I again write Euler head is equal to UO upon G. UO minus, now VFO is Q divided by pi DO BO cot of beta O dash. Okay, and further I can write it as UO square divided by G minus UO Q divided by G pi DO BO cot of beta O dash. Now further, if I run my pump at constant speed, okay, so at that very time UO is constant. So therefore again I can write HE as a constant C1 minus a constant C2 Q cot of beta O dash, where C1 is UO square divided by G and C2 is UO divided by G pi DO BO. Okay. Now you can see this relation. From this relation, I can plot how Euler head varies with the discharge. Okay. Varies with the discharge as well as with the vane shape, that is angle beta O dash. So now I can plot that graph. So you see case 1, okay, when my beta O dash is equal to 0, okay, not 0, it is 90 degree. Beta O dash equal to 90 degree. At that very case, cot of beta O dash becomes 0. So that means for radial vane, now you can put this value into above equation and write for Euler head. Okay, so Euler head is a constant C1. So you can say that for radial vane, okay, for radial vane, Euler head is constant with the discharge. Okay, so that is my Euler head is constant with discharge. Now, second case, when beta O dash is less than 90 degree, that is the case of backward curved vane. Okay, so in that case, cot of beta O dash positive. Okay, the cos of beta O dash is positive. So that means if you put this positive value into above equation of HE, so you can say that HE decreases with discharge. Okay, when my Q increases, because in that relation here is the negative sign, so you can see HE equal to C1 minus C2 Q cot of beta O dash. So here is my negative sign. So due to this negative sign, you can say when my Q increases, HE decreases. Okay. And then the third is beta O dash is greater than 90 degree. So then cot of beta O dash is negative. So my HE is equal to C1 minus C2Q cot of beta O dash. Now this value becomes negative. So negative negative becomes positive over here. So that means with increase in Q, my Euler head increases. So this is how Q, HE, and vane shape affects each other. Okay. Now if I try to plot this, on this side I have Q, on this side I have Euler head. You can see it is a straight line. When beta O dash is equal to 90 degree, this is sloping down. When beta O dash is less than 90 degree, and it is sloping up when beta O dash is greater than 90 degree. Okay, so this is my variation. So now you can also say the head generated, that is HE, is more in case of forward curved vanes. Okay, so HE is more in case of forward curved vanes.